Kielak, and he's talking about the computational approach to the homology of SF3.
Yeah, thank you very much. Thank you for the invitation to speak here. I have to say I feel very intimidated talking about property T and related things here with this audience. Fortunately, some of the most scary people have left, but many others can here. So, yeah, be gentle with me. Okay, so I want to start. So, I mean, I am going to repeat many things that were already said in this conference. Okay, so for people who fell asleep at various stages of various talks, maybe it will be a nice recap. Otherwise, you might be a bit bored at the beginning, but I mean, I think I have to say certain things. So, the first thing I want to do is I want to define property T, and I'm going to do it in a cheating way, as many other people did in this conference. So, a discrete group G has hash downs property T. If and only if the first cohomology of G with coefficients in a representation, unitary representation on a Hilbert space is 0. So for every unitary G rep, okay, it's a Hilbert space. So, of course, we all know this is a celebrated theorem of the Longuet-Chartet, but I am going to cheat and use it as a definition.
You should at least put countable.
Countable? Yeah, sorry. Thank you.
Some extras didn't believe
Okay, countable. Thank you. I mean, anyways, you know, this is the central player here, so it is countable. I mean, finitely generated, in fact, is what I mean. Okay, right. Now, so this is kind of funny because we're starting at looking at cohomology in degree 1, and why shouldn't we start at degree 0? Well, part of the reason is that this is a well-understood object, right? I mean, this is just the G invariance of the Hilbert space. In the end of the day, we all know that cohomology is just the derived functor of taking invariance, right? So it's natural, but it's kind of interesting because this fact, I mean, so this can either be 0 or not, right? So it is 0 or it isn't. And somehow this distinction will carry forward. So we will have to differentiate between looking at unitary representations with and without invariant vectors. So this guy will play a role. Okay, and somehow straight away we can move on to higher T. So this is the definition due to Bader and Zauer. And I should also say, all the Baders appearing in this talk, this is always Bader Senior. The Bader Juniors will not play a role yet. Hopefully, they have the role to play in the future developments. Okay, so Bader Senior and Zauer, and two definitions. So G is going to have property Tn, round brackets, if and only if, copy it correctly, cohomology of G with coefficients in some unitary representation is 0 for all I smaller than n, and all h's such that there are no invariant vectors. So because of this, we can really say for all I smaller than n, this includes 0. Now there's another definition. G has the square property Tn if and only if we have vanishing of all of those cohomologies for every I between 1 and n. Okay, that I no longer require no invariant vectors. Yeah, so it's clear that this is stronger. Okay. And as was already said a number of times, for 1 they are the same property. Okay? Okay. Right, so what this talk is really going to be about is going to be about establishing these properties for, or trying to establish these properties for Sn and Z for various values of n. And now, when we started thinking about this, I think the paper of Bader-Zauer, in which they actually did prove, certainly, let me write it down, theorem. Okay, so this in the lowest case goes back to Kasztan, otherwise it's very sour. SLN Z has the round property Tn minus 2. Okay, correct? No complaints? Okay, so when we started working on this project, this was either not yet on the archive, or at least we didn't know about this. So when we started working on this project, we were hoping to be able to maybe establish something like this a weaker for groups SLNZ. Okay, but then in the meantime, Roman and Uri proved the theorem. So then you start wondering, okay, what can we do with what we have? So this is an example of vanishing below rank. Below rank, which is equal to n minus 1. So then you have, the remaining question to answer is what happens at the rank. Okay, so you want to understand what this is. Okay, that's the question. Okay, so right, so how do you actually compute cohomology? I need to give you a bit of a crash course in computing cohomology. So how do we compute? Okay, how do you compute cohomology? So you start with a resolution of the trivial CG module C by projective modules. Okay, I guess we all know this. So what does it look like? Well, I have C here, and I'm going to have some C0, C1, and Ci's projective. So this is exact, I should say, this is the exact thing. And the Ci are projective CG modules. Okay, so if you really want to compute, for example, using a machine, if this is all you have, then you are already lost, okay? Because there is no way of computing with anything which is not finitely generated. So you have to hope that all the CIs are actually finitely generated. Okay, so that's a hope. Okay, so now what do we do? So to compute, maybe I'll go to the left. So to compute cohomology with coefficients in a Hilbert space, but in general, if you want to compute cohomology with coefficients, you tensor. Well, actually, I'm going to compute homology and cohomology. Let me do homology. We now tensor with H. So what do we get? We have this chain. These are CG modules. This is a CG module. We tensor over CG. I should have taken homs, but because everything is finitely generated, we are within our hope. It doesn't actually matter if I tensor or take hom. Blah, 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 and then we end up at C0. Then we no longer care about this copy of complex numbers at the end. Okay, so that's what we do. We have differentials. So there used to be differentials on the level of these CIs. Now we're going to tensor them with identities. And so what we also have, because we have a Hilbert space here, we are going to have, well, actually, we always have them. We have codifferentials, okay? So codifferentials go the other way. How do we get them? So the differentials are matrices over CG. Okay, I'm cheating again. So assume that the CIs are actually also free. Okay, just for simplicity of discussion, they're free and finite generated. So the differentials are just matrices over the group ring, and the codifferentials are obtained by applying the star, right? And what does the star do? So if you take a group element, the star returns its inverse. For matrices, you do transpose and you apply star to every coefficient. For lambda in complex numbers, you get. Okay, so there is a kind of a nice, easy algebraic way of building these matrices out of these matrices. Okay, this is all standard. Okay, so now comes something slightly non-standard. So because we want to compute the cohomology with these coefficients, I didn't say it, but we are computing the reduced cohomology, so the Hausdorff cohomology. This was mentioned a number of times. Normally, I would just take the kernel of the codifferential, let's say I, and divide it by the image of the previous codifferential. However, if I do that, I'm not going to end up necessarily with a Hilbert space, so I'm going to take the closure as the reduced cohomology. Okay, but now here comes the magic of Hilbert spaces. There's an alternative way of doing this. And the alternative way involves the Laplacian, right? So it turns out that this reduced cohomology of our group with coefficients in the Hilbert space coincides with the kernel of the Laplace operator. Okay, where this guy is partial star plus partial star partial. Okay? So if you haven't seen it before, this is the Hodge-de Rham decomposition. It's a beautiful exercise. Okay, and it deals with this reduced business. So it's only when you consider reduced cohomology do you get the equality between the cohomology and this kernel. Okay, but this is kind of a cool thing, and I don't know if this is appreciated enough. So when you take cohomology of coefficients in a Hilbert space, everything becomes very local. So everything happens just in one dimension. Okay. Normally, when you look at cohomology, you have to look at what comes from dimensions below you. Yeah, it's kind of a process. You start at the bottom and you keep going. With unitary coefficients, you don't have to do that. Everything happens in one dimension. And I think this is also part of the reason why people never mention this h upper 0. So in usual group cohomology, if you have vanishing from the very bottom with 0 up to some point, you get to build chain contractions that are very useful to do things. Okay? With unitary coefficients, I've never seen them being used because of this. Somehow it's all dimension by dimension. They don't interact in the same way. Okay, right. So this is the Laplacian. And the game is about understanding its kernel. Right. Okay, so remember the game, or the aim of what we started doing was to prove the vanishing of cohomologies of Sn and Z with some coefficients, which means that we wanted to prove that this kernel is trivial. That was the goal. So how do you do that? Okay, so how do you prove the vanishing of the kernel of this? Okay, so this it depends on h. Right? This is it on h. Okay, so you want to do it for all h's, and here is a way to do it. So as I mentioned before, the Laplacian itself is a square matrix over the group ring, okay, the group algebra CG. So imagine that it so happens, so suppose that there exists a lambda, a real positive constant, such that I can take the Laplacian, I can subtract lambda times identity, and I'm going to see it being equal to the following expression. Okay, this is where the xi's lie in the matrices. Imagine that I did it. Okay, this of course showed up in Piotr's paper. So imagine that I found such a sum of squares decomposition for Laplacian minus the identity. Well, what happens? Okay, so well, let's just do an easy computation. So if I take V lying in the kernel of the Laplacian, then what happens? Well, so let's see. So I have minus lambda times the norm of V. Okay. This is nothing else but delta I minus lambda identity V comma V, right? Because delta IV is 0, so I get minus lambda. I could take it out, it's the L2 norm of V, so nothing happened here. But now I get to use this guy. Okay, I get to take the sum out. I get to put this guy on the other side, then I get the sum of norms. The sum of norms is non-negative, but that is definitely a negative number unless it's 0. Okay? Yeah, everybody happy? This is a very easy computation. It shows why sum of squares give you positivity. So if this is true, this is non-negative, this is non-positive, so V is 0. Okay, so if you are in this lucky situation that you can actually subtract a little bit of identity from the Laplacian, find the sum of square decomposition, then you are definitely happy. Your kernel is going to be 0. Yeah? And of course, this must have been known for a long time. It must have been known, at the very beginning of time, but somehow nobody really investigated this property very seriously until Taka showed that, at least in rank 1, this is essentially equivalent to property T. Okay, it seems much stronger. This could have been, people could have tried to do that a long time ago, nobody bothered, okay? So the psychological difference was that Taka showed that actually this is equivalent to property T, well, a version of this is, I'm going to say it properly in a second, a version of that is equivalent to property T, so this is exactly somehow the right thing to do. Okay, so let me write down this as an actual statement. So here's the theorem. This is due to Zawa, and then it's Ada Novak, and there is an input into the statement from Badazawa. Okay, so the statement is the following. H1 G H is 0 for all H's. This is Ozawa's theorem. If and only if delta 0 squared minus lambda delta 0 admits such a sum of squares decomposition for some lambda bigger than 0. The fact that so this is not the same as here. The fact that we have to do delta 0 squared minus lambda delta 0 has to do with the fact that we are allowing all sorts of representations, including ones which have invariant vectors. Okay, that's the reason. In higher rank, you don't have to do that. In higher rank, so I is now bigger than 1. This is the same as delta I minus lambda delta I being a sum of squares. I'm writing the same symbols, but they really mean different things because they're matrices of different sizes. But that's not super important.
Is it really minus lambda delta I?
Yeah, sorry, it is. Yes, sorry. Thank you. Absolutely. Thanks.
It's squared.
Squared?
It is squared. Well, you don't know this one.
It's not squared. I think it's okay. Okay, right. So this is where we knew that. We didn't know about Badazawa. We wanted to prove something like this or weaker. So we thought, okay, well, how do you do that? So the beauty of this approach is that you can really do it using a computer. Okay, because there's only finitely many of disk size. It doesn't matter which level you are. We had some delta in some level I. There's only finitely many of disk size. Each of them is a finite matrix over the group algebra, so it has only finitely many group elements involved. Okay? So if you can guess what group elements to use, you can ask your computer to do this computation for you. Okay? You say, dear machine, here are the group elements I want to use. Just solve it. And computers can do it if you guess correctly. If you don't guess correctly, they will not solve it, and that doesn't tell you anything. Okay? So, when we got everything ready for the computations, we found out about the Badezawa paper. So we knew that we have to start trying at the rank. That's the lowest thing. Go ahead.
So you were saying you guess the group elements. Do you also guess lambda?
You can compute. Yes, in principle you should guess lambda, but in reality, machines can do it for you. They can optimize the lambda. And there's one more thing I should say. So as I said it, let's say that you guess the lambda, you guess the group, the support, and you just let the machine solve it. In theory, you could do it fully algebraically. Okay, so just actually solve it. In practice, it never works. You have to do it numerically. And when you do things numerically, you don't have an inequality, you have an almost equality. It's an equality up to the errors that the computer made. Okay? But it so happens that you can pay a little bit of a price, you can decrease the lambda a little bit and go from a numerical almost solution to an actual honest-to-God solution. That's important. Okay? So once you guess the support here correctly, you can just do your numerical computations, which is something there's software which does this for you, and then at the end, if you get a numerically very accurate solution, you get an honest-to-God mathematical solution. Okay, so that's how we proved property T for odd F6, for example, and how Ozawa, Novak, and Kaluba proved property T for out of 5, yeah? And Nietzsche for out of 4. Okay. So that's what we were trying to do. So we had our, the machine was ready, the resolution was there, we wanted to compute, and we started doing this, and we tried to guess the correct supports, and it didn't really want to work. Okay? So, right, so the first thing that came to my mind was this famous quote of Homer Simpson, who says, "Children, you tried and you failed. The lesson is never try." Okay, but then we decided to try, and so we kept trying, and it didn't work. And then at some point we thought that, well, I mean, one reason why it's not working could be that we have guessed the wrong support. One reason that it's not working could be that the numerics are too subtle. Somehow you cannot get a good enough approximation. But there is another reason why it could have worked. It could have not worked, could have failed. Namely, it might have just been not true, right? So, and then we investigated the other possibility. Yeah, so this is all joined with Benny Brook, Sam Hughes, and Piotr Mizerka. And it turns out that for small values of n, SLNZ does not have this property Tn minus 1. It doesn't have the weaker property, which is the stronger statement, right? That's right. Okay. Okay. So it could have never worked because it just wasn't true. And more concretely, in fact, so if you show that you don't have this higher property T, we actually exhibit explicit representations which witness this. So concretely, there exist finite dimensional orthogonal representations without invariant vectors, and trivial invariant vectors, with the cohomology so it fails on relatively well-behaved representations.
I'm a bit confused because in that board you did not make the assumption that H has no invariant vectors, but now you're giving a theorem about the
So if you falsify something and your representation has extra property, that's just stronger, right? So I'm telling you that it's false, and even if you decided to look only at representations without invariant vectors, it will still be false.
But like, could it be like if that criterion is about vanishing for all representations, and you have non-vanishing in for trivial?
Okay, I see. Okay, did I write it wrong? Let me think about it. This, let's see.
You should assume no invariance.
Should there be still no invariance here? That's what I got wrong. Yeah. Okay. Sorry. Sorry. Yeah, that's right. Thanks. Okay. Right. So, I mean, I will tell you roughly how we. Okay. So, I can tell you in one sentence how we got this representation. It's a brute force search. Okay, but I will elaborate on it a little bit later on. But before I do that, I wanted to tell you how you can get some bad news using actual maths and not search. So what happens for even smaller values of n? Right. So what happens for n equals 2? We all know what happens, right? There's no property t. Why isn't there property t? Because SL2Z is virtually a free group, right? So it's virtually Fm. And now, how do you produce a representation that violates what you want? There's an obvious choice. And we all know that we can take the reduced first cohomology of the free group with its own L2 coefficients, right? What is it? Well, once I do know something here, actually, this is L2 homology after all, so it is exactly m-1 copies of L2 of Fm. This is an isomorphism of Hilbert modules. So in particular, it's not 0. Okay, m is strictly greater than 1. Okay, so for this finite index subgroup, we produce a representation without invariant vectors. How do we go back? Well, of course, the fancy way to say it is we do Shapiro. So by Shapiro's lemma, you can co-induce from Fm to SF2Z. And this is still not 0. Okay, and co-induction is the same as induction in this case because this is finite index. So it doesn't matter. Okay, so that's, we all knew this. This is how you prove that free group doesn't have property T. So this is the easiest thing, and this is exactly the non-vanishing at rank because the rank is 1. Okay, now what happens for n equals 3? So for n equals 3, you can get almost to the theorem I stated, but not quite, without any serious computations, or rather using classical series computations. Okay, so how does that work? Okay, so we do know that there exists a finite index subgroup which is torsion free. Okay, and now what do we know about the cohomology of this G? So, well, first of all, I'm going to look at the cohomology of G with trivial complex coefficients. Well, this is always a copy of C. Yeah, so there's something sitting there in dimension 0. In dimension 1, we have nothing because of property T. Okay. Now in dimension 2, well, God knows, yeah, there's something potentially there. I don't know what sits in dimension 2. But what about high dimensions? This is 0 if I is strictly greater than 3 because of cohomological dimension. Okay, since cohomological dimension of G is okay, so we have some cohomology 0, nothing here, potentially something here. Here it's always 0, and we care about H upper 3. Yeah? So what is missing to allow us to compute? Well, we need to know the Euler characteristics. So there is a theorem of Harder from 71. And this, as far as I know, is the first computation of Euler characteristic of the rational Euler characteristic of SL3Z. This is 0. Okay, this is the rational Euler characteristic. So the Euler characteristic of G is 0 as well. Okay, so now let's compute. So we have 0 on one hand. On the other hand, we have one dimension in 0. We have mysterious number of dimensions here. And we're going to subtract, well, nothing for here. And we're going to subtract the dimension of H3. Okay? So this is at least 1, so this has to be at least 1. It's not 0. Okay? So this is something I've learned from Roman Zala, by the way. So it's a very, very cool trick. Okay, so because you have some finite index subgroup with trivial coefficients giving you non-zero cohomology, you do the same induction thing as before. And this tells you that this guy, I seem to have gotten something. I'm worried about my ranks. This is the induced representation. It is not 0. Okay, so what's the conclusion? Okay, so that means that SL3Z has no E3. Okay? This representation does have invariant vectors, yeah, because we start with the trivial representation of finite index subgroup. When you induce that, you always have invariant vectors. Okay, so this is what you can get without using any computers. If you want to get to this theorem, you actually have to really construct something explicit. Okay, so now let me tell you how this is actually done. So, computing the resolution. So, in order to be able to employ a machine to do some brute force search through some representations, I need to be able to get the actual resolution explicitly so that I will be able to tensor and do the computations. So that's something. And this turns out to be computationally very, very difficult. Okay, so I will explain what we do. This is an idea that goes back to at least 1980s. So we haven't done anything mathematically new here. But so the way it goes is that we look at the Voronoi complex. Of the bodification xn star of the symmetric space xn of epsilon r. Okay. Relative, so we are looking at the Voronoi complex of modification relative to its boundary. The boundary, which is the modification take away. Okay, so what's the story here? So Voronoi actually introduced his tessellation in 1908. Or at least this is when the paper got published. This is actually the same year that he died, age only 40. So, so he introduced this tessellation. Out of the tessellation, you can very quickly get it essentially is a CW structure on the nose. And it's all very, very explicit. So, so you can hope to be able to run computer code to really compute this cell decomposition, okay, and the differential. So this has been done.
Not by Voronoi.
Not by Voronoi. Not by Voronoi. So I think the first person to do it is Soule. The paper appears quite late, I think in, do I have a date? I don't have a date. But I think he did it in the 80s and the paper appeared around 2000. I think that's roughly right. So, but now it's interesting. So, Soule was interested in computations and K-theory. So when he computes, then other people later, when they computed these complexes, they did certain simplifications straight away because they knew it's not going to influence the computations later on. Okay? Whereas for us, we really need to do the honest computation of the full thing. So to the best of my knowledge, we were the first people to actually code in the complete computation. But of course, we haven't really done anything original. Okay? It's just the obvious thing. And now the interesting thing is that this, even now, the highest dimension in which this has been done is 7. Okay? Even in dimension 8, for SLN, I mean the rank, so I mean the n. So as for SL8Z, the computations are too involved for modern computers. Okay? So whenever you try to do something computational, you immediately realize that exponential growth, which somehow mathematically you think you have wrapped your head around, is a monster. Okay? If you have exponential growth, you cannot really compute anything. Yeah? It's only the very, very smallest things. Yeah, so even so this has been done up to n equals 7. Okay? So in practice, otherwise it's a no-go for now. Okay, so this is the complex, and what you want to do, I should give it a name, just to borrow the complex. Okay. There are some kind of subtle issues with it. For example, these modules are not free because you have torsion inside SLNZ, and this torsion stabilizes certain cells, and you have to worry about it. So there's some level of technical annoyance in all of this. But of course, it's not mathematically interesting. So you have to. I mean, these guys really will be projected. So that's good here. Okay. So what's the next step? So I promised to give you a resolution of the trivial CG module. Well, that's unfortunately not what you get here. So this is a chain complex that you can actually compute, but it's not what you want. But it turns out that if you take this chain complex and you tensor it over the group algebra with some module M that you want to compute homology, say cohomology in, and you look at the homology. That guy, this actually is homology of SLN Z with coefficients in, and here is the annoying thing. There's something called the Steinbeck module, and you have to tensor that with your M. Okay? So what we would like to do, I mean, I know we are looking at cohomology, but if you are interested in homology, you would like to have the M here. Unfortunately, you get this Steinbeck module showing up here. So that's life, but
so this is a resolution of the Steinbeck.
It is a resolution of the Steinbeck module. That's right. Yeah, that's right. So we had to work a little bit to prove it actually. So it wasn't all done by. So the fact that if M is trivial, that you get the Steinbeck module here, this is due to Soule. But in this generality, we had to do a little bit of yoga to get it. But that's true. And then there's the last bit, namely, thanks to the Borel's duality, the Steinbeck module is actually not a problem because the homology of this, or rather this homology, is actually the same as the cohomology, and now the numbers right, n minus 1 over 2 minus I of SLNZ with coefficients in the module M. Okay, so in homology the situation is complicated, but in cohomology it's totally complicated. Get rid of this step. Yeah? Okay, so this is what we Okay, so what did we do? So we we had to rebuild this Voronoi stuff because we wanted the full picture with every single differential being exactly what it should be. So we did it up to n equals 5. And then if you want to go beyond 5, you actually have to start really worrying about how efficient your algorithm is. But that has been done to dimension 7, not by us. And then once you build it, what we did was we looked at finite quotients.
Sorry, wait, who's
Yeah.
M?
I'm sorry?
What's M?
M?
M.
Where is M?
The tensor or something.
Oh, the big M. Sorry. Yeah. Sorry. This is a module. So this is SL and Z module. Sorry. Okay. Any module.
Any module?
Yeah. So that's not in Soleil. That's another thing. Right. So what we did? So we actually looked at finite quotients of SL and Z, and for these finite quotients, I mean they're finite groups. We looked at irreducible representations which are not trivial. We pulled it back to a representation of SL and Z and ran the computations. Okay, and we did it some number of times, and then the answer came out that well, sometimes it doesn't vanish. Yeah? So that's how working with computers is. So this is why our representations are finite dimensional, because they actually come from finite dimensional representations of the finite quotients. Moreover, because they are finite dimensional, there's something I was sweeping under the carpet. In the initial discussion, we were looking at reduced cohomology, whereas this guy here is the unreduced cohomology. This is the usual algebraic cohomology. But of course, because M is a finite dimensional representation, it doesn't matter. Yeah? When your Hilbert space is finite dimensional, everything is closed, and you don't have to worry about it. So this came to our rescue. Okay, so we did it for n equals 3 and 4, and it worked. For n equals 5, we started doing it, but it was taking a long time to compute. And then we also got demotivated because, I mean, you prove it for 5 and so what, right? I mean, it doesn't really improve your understanding of the situation. So, I mean, I would say there's an obvious conjecture here that at rank you should have non-vanishing. We don't know how to prove it. I mean, we don't have any idea how to attack it even. We only have this computational evidence in very low dimensions.
So there's this conjecture by Church, Putnam, and Farr, where they conjecture the vanishing of this cohomology in low codimension, which would correspond, I think, to low degree homology vanishing. Do your computation, I mean, can you tackle this with your?
We haven't tried.
I think it's about the trivial representation. Not completely sure. But it seems should be almost easier because it's about the low degree homology.
Yeah. I mean, I don't see why not. But I mean, for trivial coefficients, this has already been computed by Soleil and co-authors. So.
In low degrees.
To be honest, I don't remember. Yeah. So I couldn't. Yeah, I mean, I don't see why not. I mean, the code is all there, and one can run it and check it. Yeah. There's no reason why it wouldn't. And for n equals 3, this is all small enough and runs quite quickly. Yeah. Anyway, so I think this is finishing up 5 minutes early, but this is all I wanted to say. So thank you.
Thank you, Dawid. Other questions?
So these finite quotients, are they Z mod PZ for prime or?
Yeah, I think we passed to SL and Z mod 3, mod 5, yeah, something like that. Yeah.
Do you know which of these beautiful representations give you this non-vanishing?
No, we only found the first one that worked, and we stopped searching. So we don't have any classification of which ones work. Or yeah, I mean, to really answer any question about any infinite problem, you have to understand what's going on, right? And computers, as Picasso famously said, they are useless. They only give you answers, right? So. Yeah.
But do you know which
Which
of the irreducible representation of SL3 Z mod 3Z is responsible for this?
Yes, we know exactly the one that is responsible, yes. Yeah, that's in the paper, yeah. But we have not checked beyond, yes.
One of the ingredients in Bader-Sauer is polynomiality of a filling invariance below the rank by Leipzig and Young. So reverse engineer and prove that these invariants are non-polynomial at a rank, which is known, but
so I understand correctly. You start with this particular representation, you feed it back into the.
one of the ingredients they use is that all the Fielding invariants are polynomial below the rank, and also other things which higher homological properties which are okay. But the thing, my question would be, conversely, can you deduce that the Fielding invariance is non-polynomial at the rank?
I don't know. So I mean, I guess one would have to see exactly in your guys' paper, right? In Badazauer, how it's.
The thing is that you know something about the non-vanishing of the cohomology for certain representation in the rank for the Lie group, but because we don't have this polynomial Dehn functions 1 degree higher, we cannot conclude what you did for C.
Okay.
Yeah. But okay.
But maybe I should mention that I mean for SL3R at the rank we know non-vanishing. So this also for for co-compact lattices it would be known. For SL3Z we cannot deduce it because of this lack of polynomiality. But also it doesn't say anything. I mean, if we had polynomiality, we would expect non-vanishing.
More questions? No? Let's thank Dawid again.